Right now, the industry is flooded with fragile AI wrappers and toy demos. They look flawless in a sandbox, but hitting reality, that illusion shatters. Put a model in front of an email thread with 10 forwarded headers, a scheduling conflict, and a messy data stream, and the context evaporates. The continuity breaks. When an enterprise AI deployment collapses, it usually happens in one of three distinct ways. A privacy lock is breached, leaking sensitive user data to the UI. A single server timeout cascades into a total system outage. Or the database memory wipes completely blank, forcing a human to step in and rebuild the state from scratch. The initial reflex is to patch these probabilistic errors with brute force. Developers attempt to fix the privacy leak by duplicating the entire database. They try to prevent the server outage by purchasing expensive premium infrastructure, and they fight the amnesia by endlessly expanding the prompt's context window. Surviving production requires dismantling these three anti-patterns and surrounding the probabilistic model with strict deterministic engineering guardrails. Consider a financial advisor conducting a live screen share with a prospect. If they ask an AI assistant to search their book of business, exposing a specific client's name or exact assets under management, or AUM, is a catastrophic breach. AUM refers to the total market value of the investments that a financial institution manages on behalf of clients. Teams often solve this by building a secondary anonymized search index parallel to the main database. But a second index forces two ingestion paths and schemas. Eventually, logic drifts. Worse, stripping data alters search rankings, making the output technically private but practically useless. The reliable solution is a unified search pipeline. Results rank normally, but pass through a strict redaction gate controlled by a toggle. This gate maps identity points to stable alternatives, like converting client Smith to client A, or binning AUM into rounded ranges. Decision-critical structures, like locations and certifications, pass through untouched. There is still a hidden vulnerability. If the model is fine-tuned on raw firm names, it can leak those strings from its latent memory. Fine-tuning is the process of adapting a pre-trained AI by training it further on a specialized dataset. To close this leak, that training data must align with the exact same mapping rules used by the redaction gate. Redacting identity while preserving the underlying structure keeps the system operational and builds absolute user trust. A similar trap exists with system resiliency. Engineers often treat a cache, a temporary storage layer meant purely to optimize performance, as a hard dependency. When that happens, a single timeout in the cache cascades into an application-wide crash. The standard reaction to this instability is to purchase premium, high-availability caching tiers to mask the underlying fragility of the application code. True resilience means cache operations can fail and return a null value without retrying. A circuit breaker tracks failures, opening after 5 strikes. Queries then bypass the cache entirely, routing to the main workflow. A 5-minute cooldown timer ticks down before a single test connection attempts recovery. Premium infrastructure tiers often charge $440 a month, primarily for built-in hardware redundancy. Because this circuit breaker handles that redundancy in the application code, the system maintains uptime on a basic $16 a month instance. Moving the responsibility for uptime from the infrastructure provider to the circuit breaker code eliminates the need for expensive redundant hardware. The most expensive failure mode in enterprise AI is Amnesia. When a session resets, the model forgets everything that happened previously. Users then spend hours manually re-explaining project architecture and task state. Developers often attempt to fix this by stuffing tens of thousands of tokens of static documentation directly into the system prompt. This creates severe secondary problems. Static context rots as the project evolves. The bloated prompt increases the rate of hallucination, and the massive payload exhausts the token budget before the user even types a command. Managing memory as a 4-layer infrastructure stack decouples compute from persistent state. The foundation is the database task ledger. Next, progress files capture in-flight reasoning. The third layer holds session handoff documents to survive hard resets. Finally, the infrastructure API feeds environment variables directly to the system. Connecting this stack is a mandatory boot protocol, a rigid, deterministic checklist that forces the system to sequentially query all 4 layers before a new session begins. The system structurally bars the AI model from generating a single output token until this state recovery script completes. Anchoring Project Truth in a rigid server-like boot sequence maintains session continuity regardless of the conversation window's limits. A language model generates highly capable output within the specific frame you provide, but it has no awareness of system time, infrastructure outages, or data leakage risks. To survive contact with reality, the unpredictable core must be completely surrounded by a rigid, geometric outer ring, comprised of the redaction gate, the circuit breaker, and the boot protocol. These three deterministic systems work in concert. They catch identity leaks before they hit the screen, route around failing nodes before they crash the application, and restore state before the model can hallucinate a blank slate. The AI model writes the response, but the rigid system architecture carries the timeline. Surrounding a probabilistic tool with strict engineering guardrails is the only way to deploy high-stakes workflows. A language model generates highly capable output within the specific frame you provide, but it has no awareness of system time, infrastructure outages, or data leakage risks. To survive contact with reality, the unpredictable core must be completely surrounded by a rigid, geometric outer ring comprised of the redaction gate, the circuit breaker, and the boot protocol. These three deterministic systems work in concert. They catch identity leaks before they hit the screen, route around failing nodes before they crash the application, and restore state before the model can hallucinate a blank slate. The AI model writes the response, but the rigid system architecture carries the timeline. Surrounding a probabilistic tool with strict engineering guardrails is exactly the only way to safely deploy these high-stakes workflows.